Yeah, this just to show what they are and where they are. That's it. Um, laser. Yeah, I don't know. I don't think it's part of that, but I don't know why there's a laser there. I don't know.
Marketing given.
Huh?
Marketing given.
It says US only also, so I don't know. How does it?
That might mean it's using the empirical system. Is that what it means?
Sorry, what?
Does that mean it's just using the empirical system, like US only?
I don't know.
Something about losers. Only in the US.
Yeah, I don't even know what it'd be used for. Because autofocus is usually IR, I think. It uses like a distance. That's what it's for. Like it, yeah. Or it does depth with IR. So that's how it focuses. But
Such a slow wave that it can bounce and then it takes how long it takes to travel back.
I don't know. I think it kind of paints the surface with the IR, and the distance corresponds to how much energy gets to that surface. So it can see the, I don't know. Depth is usually IR, so yeah, I have to guess it's based on distance. The farther away, the less that surface will absorb IR light and then re-emit it, and so it'll see it darker. I don't know.
Fair enough.
Alright. But any of those 3D cameras, like the Kinect, or like any of the Windows Hello that's built in now that see depth, it's IR. They have to have the IR camera. All right. All right. We are going to go over molecular orbital theory before we do the review. And I decided yesterday with the other class that we're not going to put this in the final. So you might think, why are we going to go look at it? Well, I wanted to just bring this up because it's going to fill in some holes in the current model of bonding that we've learned so far, okay? So valence bond theory, that's the current model we've been learning. In valence bond theory, that describes how orbitals overlap to make these covalent bonds. So we've learned already a little bit of a complicated part of valence bond theory, the hybridization idea that orbitals mix together to make these new hybrid orbitals that point at different angles. That makes all of the different shapes. But we've also seen, and so Lewis structures is all part of valence bond theory. But we've seen some failures of Lewis structures. So first is resonance. The fact that we have to do resonance and come up with these resonance hybrids. A resonance hybrid is not a proper Lewis structure. So if I want to do the true picture of benzene, that 6-membered ring with 1.5 bonds, I can't do that with Lewis structures. I can draw the two resonance structures and say, oh, it's actually a combination of them. So that's one failing of valence bond theory. And there's plenty others. God, I can't think of it off the top of my head. So here's one. So remember when we learned about paramagnetism and diamagnetism? So paramagnetism, diamagnetism, that happens, you get paramagnetic material when you have unpaired electrons. And we looked at paramagnetism and diamagnetism with respect to atoms. So nitrogen, for instance. You look at the orbital diagram for nitrogen, right? It's got a 2s and a 2p, and it's valence orbitals. Nitrogen has 5 valence electrons. So there's some unpaired electrons. So we would say the nitrogen atom is paramagnetic. It is attracted to a magnetic field. That's what it means to be paramagnetic. If it's diamagnetic, all paired electrons, it is not attracted, actually slightly even repelled by a magnetic field. Well, what we did back then was only look at atoms. We didn't actually talk about molecules. And I think I've shown you something similar to this, but I wanted to show you this one because it's nice high res, nice colors, and it's a cool experiment. So that's liquid nitrogen right now.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
The boiling, the liquid nitrogen boiling, you got a warm pipe, but it's cooling down. Liquid nitrogen is actually slightly colder than liquid oxygen. So you can make liquid oxygen this way. So they just open the gas tank, oxygen is flowing through the tube and getting liquefied as it goes along. There it is. The laptop's up the way it is down there. Dewars are double-walled glass containers, so there's a vacuum in the middle, so it's nicely insulated. They're very expensive. They fall over the cathode. Notice how it's like lightly blue. Liquid oxygen is slightly blue. So they're pouring liquid nitrogen through. So the molecule N2 is not being affected by that strong magnetic field that's right here, which is different from atomic nitrogen, right? Atomic nitrogen is paramagnetic. What we're seeing is liquid nitrogen is diamagnetic. And here's liquid oxygen. it's fizzing because it's, you know, hitting a warmish magnet, it's boiling away. But as it cools down the magnet, it's going to stay longer. More. Yeah, it's getting stuck right between that magnetic field. So liquid oxygen is paramagnetic. So this is diamagnetic, and this is paramagnetic. All right, so again, ignore this part. This is atomic nitrogen. So, how do we know, I mean, how do we predict this? Like, we can measure this in an experiment. How do we predict this? And so here is another failing of the valence bond theory. So there's your Lewis structure for oxygen. I don't see any unpaired electrons in there. Everything's paired up. But we know that there's unpaired electrons in there because it's paramagnetic. So this is yet another, like I said, failure of valence bond theory. So Lewis structures cannot show us the fact that we can't predict using Lewis structures or valence bond theory that oxygen O2 would have been paramagnetic. So this is where we have to turn to a new theory for bonding. There is a different way to approach this. It's less intuitive because it's less visual. Lewis structures are nice, they're very useful, but it doesn't do everything. So molecular orbital theory is better for when you're working with energies and stuff like that. And we're just going to touch the surface. I just kind of want to show you this. Like I said, we're not going to have it on the final, but it's going to be like week 2 of Chem 222. So in Chem 222, the first topic is going to be inorganic bonding, or not inorganic, ionic bonding, which you guys know already, even though you haven't learned it yet. It's all Coulomb's law based, charges attracting. And then immediately after that, there'll be metallic bonding. And in order to understand how metals are conductive, how they bond, all that, you have to understand molecular orbital theory. So it's going to be a crash course in 222. So let's understand. So to get to molecular orbital theory, we have to go back to basics. We have to remember that wave functions, these equations that give us the orbitals, are a way of treating electrons like a wave. A three-dimensional wave, but a wave. So let's simplify further and go back to one-dimensional waves. And remember that when you have two waves, and if they're in phase and we combine them, like they cross paths, and they're in phase, they will constructively interfere. They'll become bigger. If the two waves are out of phase, like this, where peak, trough, and they overlap, they will destructively interfere. And it turns out the same applies to orbitals. Even though orbitals, we don't really think of them as having a phase, they do. These are wave-like, they're waves. So they have a phase too. And here's how this works. So we're going to start with the simplest of molecules, that's H2. 2 hydrogen atoms. So each hydrogen atom, so look at the bottom part first, each hydrogen atom comes with a 1s orbital. There's a single electron in that 1s orbital. And we already know from valence bond theory to bond, they have to overlap. That's how they share electrons. But instead of just saying they overlap and it makes a bond, we're going to do something different. We're going to do something like we did with hybrid orbitals. So remember, hybrid orbitals, we took the atomic orbitals on one atom and mixed the s and the p orbitals together to make new hybrid orbitals. Well, we're going to do the same thing, but instead of doing it on one atom, we're going to do it on multiple atoms. Just 2 in this case. So I'm going to take the s orbital from one hydrogen and the s orbital from another hydrogen, and I'm going to mix them together. And the rules are the same. The number of atomic orbitals I use to mix together, I'll get the same number of new orbitals out of that. So if I mix 2 orbitals together, I will get 2 new, what we're going to call them molecular orbitals. Because these are orbitals that are now spanning the whole molecule, not just one atom. And so if these have a phase, just like these have a phase, the way you can combine these 2 orbitals, let's say they're in phase. Well, if they're in phase and I overlap these 2, they will constructively interfere between. And they will create what is known as a bonding molecular orbital. This one's labeled sigma because it's one of those side-to-side end-to-end overlaps. That's how I said end-to-end overlaps. Well, the other way they can overlap is by destructively interfering. They can be out of phase with each other, just like these two ways are. And so if these are out of phase and they overlap, the spot where they overlap is going to cancel out any orbital, electron density. So there'll be a region of 0 electron density between the atoms. And what we call this is a anti-bonding molecular orbital, because it's actually the opposite of bonding. We're preventing electrons from being shared between those two atoms. So I mix 2 orbitals together, and I will get 2 atomic orbitals, and I will get 2 molecular orbitals. This is the typical pattern, all right? You'll get, for every 2 atomic orbitals, I get a bonding molecular orbital and an anti-bonding molecular orbital. In terms of energies, so here on our energy scale, here's the original one hydrogen by itself, which has a 1s orbital in it. Here's another hydrogen by itself, which has its 1s orbital. When they overlap and they make their new molecular orbitals, we combine them. The bonding molecular orbital is actually lower in energy than the originals, and the anti-bonding orbital is higher in energy than the originals. All right, so there's a balance here. And notice each hydrogen came with 1 electron. Hydrogen has 1 valence electron. So 2 valence electrons are present in this bond. And those 2 valence electrons will go to the lowest energy orbital, just like normal. They're going to fill the bonding molecular orbital. So what can you do with this? Well, this looks pretty boring right now. It looks like an overcomplicated way to say that hydrogen makes a bond with another hydrogen, and that's true. Another thing you can calculate is something called bond order. Well, not something, we know what this is, bond order. To calculate a bond order from a molecular orbital diagram, you're going to take the number of electrons in bonding molecular orbitals, I'm going to label them MOs, and I'm going to subtract the number of electrons in anti-bonding molecular orbitals, and I'm going to multiply this whole thing by 1/2, so divide by 2. That's bond order. So for hydrogen, 2 electrons in bonding MOs, no electrons in anti-bonding MOs, I get a bond order of 1. And, you'd be like, yeah, no kidding. We already know that, because Lewis structures tells us that. So right now, we're not getting any advantage over Lewis structures. That is so much easier, which is true. Here's where molecular orbital theory starts becoming useful. Let's kind of consider some odd combinations. So here's hydrogen on the left, 2 heliums on the right. We already know 2 heliums won't bond. Helium doesn't make bonds, period, right? Well, not really. But what about if we had a helium ion? So I take a helium that has lost 1 electron, put it together with another helium, and I make He2 with a positive charge. Would that make a bond? There is no way to figure that out using Lewis structures. Okay, this has an odd number of electrons. It doesn't work. So they all have the same orbitals. Hydrogen, helium, they both have the 1s orbital. That's all they've got. And so they'll both make the same pattern of molecular orbitals. A bonding MO and an anti-bonding MO. Bonding, anti-bonding, bonding, same thing. What's different about these is the number of electrons. H2 has 2. We did that already. So you put 1 down there, 1 down there, that's it. The bond order is going to be 1. He2 plus has 3 electrons. All right, helium comes with 2. There's 2 heliums, so that's 4. But the plus charge means we're missing 1 electron, so 3 electrons. So when I put those electrons in, 1, 2, 3, and then 2 heliums, 4 electrons, 1, 2, 3, 4. All right, well, what does this tell us? Well, I already told you we can do bond order calculations. So if I calculate the bond order of each one, again, I'll get 1 for H2. For this weirdo thing in the middle, I actually can calculate a half of a bond. 2 electrons in bonding MOs minus 1 electron in anti-bonding molecular orbitals times a half. I get a half of a bond. So this molecular orbital theory can predict that there is going to be a weak bond between a helium atom and a helium ion, which is, you wouldn't be able to figure out from Lewis structures. So this is already one advantage of MO theory. And then when you get to this thing, well, as expected, 2 helium atoms, like normal, shouldn't bond. If you look at the bond order, it's 0, meaning there's no bond. They will bump off each other, and that's it. So if they collide, they'll just temporarily overlap orbitals, nothing will stick, and they'll just fly away again. Because there's no bond order between them. So already we can see some advantage of MO theory. You can start to get some weird stuff. So here is, if you're a Star Trek fan, dilithium, which doesn't really exist, but if you tried to put 2 lithium atoms together in a vacuum, would they make a bond? And according to the MO diagram, they would. So lithium comes with 3 electrons, both of them do. Here's the 1s inner orbital, and there's the next shell, is the 2s, and then there's the 2 p's, we're going to ignore those. When these overlap, these get full, so there's 6 total electrons, 1, 2, 3, 4, and then 5, 6. If you calculate a bond order, there's 4 electrons in bonding MOs, down here, 1, 2, 3, 4. And then there's 2 electrons in anti-bonding MOs. I think I forgot to mention that in addition to the anti-bonding MOs being higher in energy, they're usually labeled with an asterisk, a star. Forgot to mention that, sorry. So anti-bonding MOs are always labeled with a little asterisk. Okay. All right, so that's something else you can't do with Lewis structures. If I try to do a Lewis structure for Li2, it'll come out a little weird. It might work actually, but it'll come out a little weird. So let's throw in the p orbitals, just to make things a little more complicated. So we have to remember that p orbitals come in sets of 3. Every atom has, every atom in period 2 and lower has 3 sets of p orbitals. And depending on the orientation, they'll overlap in different ways. So if I have a carbon next to a carbon, well, those carbons will have a p orbital that'll point at each other. And those 2 p orbitals will point at each other and overlap end to end like this. So they'll do the bonding one and the anti-bonding version, where they're out of phase. But each carbon also has 2 other p orbitals that are parallel to each other. So one's going up and down like this, they're on both sides, and they're going to overlap side to side. There's another set going in and out of the board that overlap side to side. So you get pi bonding as well. So pi bonding, and then you get the out of phase pi anti-bonding. So all of that's to say is you get some more complicated patterns for MO diagrams. So just to kind of describe what's happening here, here's your inner orbital, which we can kind of ignore. This is the inner electrons. Here are the valence. So the 2s and the 2s will overlap like we've seen, bonding and antibonding. Here's the p orbitals from each atom. So one p orbital from each atom will do the end-to-end overlap and make sigma bonds and sigma antibond. And then we have 2 sets on each atom that will do pi bonding and pi antibonding. You don't have to memorize this. Don't worry about it. But this is one pattern you'll get. So now when we talk about, well, let's look at more complicated bonds between, like, for instance, 2 carbons, 2 nitrogens, 2 oxygens. Maybe we can solve the dilemma of why nitrogen N2 is diamagnetic and oxygen is paramagnetic. So here's 2 carbons. How do we fill this? Okay, well, we're looking at the entire orbital picture, so we're going to, not just the valence. So carbon's total number of electrons is 6. So 2 carbons will have 12 electrons total. So if I fill those 12 electrons in the MO diagram, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I don't see any unpaired electrons. They're all paired. I would expect C2, a bond between C2, 2 carbons, to be diamagnetic. Yeah.
What about those other, like?
So these sides?
Yeah.
So this is what they looked like before they made the bond. So when you have the carbon by itself, that's what it looks like, and it would have 6 electrons in it. And then the other carbon would look like this, and have 6 electrons in it. After you bring them together, you get what's in the middle here. So the left and the right side is just this is what the before, that's all. We can calculate a bond order. Oh, actually, before we do that, let's do nitrogen. So nitrogen has 7 total electrons. So 2 nitrogens will have 14 total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, all paired up, diamagnetic. That predicts what we saw in the video. If you calculate the bond order between these 2 carbons, you get a bond order of 2. So this is bonding, that's bonding, and these are bonding. So 8 electrons in bonding orbitals. That's antibonding. There's the star. That's antibonding. There's the star. 4 electrons in antibonding. 8 minus 4 is 4. Times a half is 2. Bond order 2. For nitrogen, that shouldn't be a big surprise. Nitrogen has a triple bond when we do Lewis structures, and this agrees with it. You get 10 electrons in bonding orbitals, 4 electrons in antibonding orbitals. 10 minus 4 is 6. Half of 6 is 3. But what Lewis structures doesn't show you is that this is going to be diamagnetic for sure. All paired electrons. So on this page, we are removing all of the side stuff and just showing in the middle. Okay? So it's just a little bit of a shortcut. So here is the C2 before, here's the N2 before. We're showing in the middle. And it's also just the valence orbital. So we start at the 2s, not the 1s. So look at oxygen. Here's the pattern you get for oxygen. Oxygen valence electrons, oxygen comes with 6 each. So 12 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's those unpaired electrons. There's the reason why oxygen, O2, is paramagnetic and is attracted to magnetic field. So if you see, hey, boron, B2, it's paramagnetic. If we tried to do that, we would see that it is attracted to magnetic field. So there's a little bit of weirdness here. You know, when you go from nitrogen to oxygen, the energies of these 2 swap places. Notice that it's now the sigma 1 first, then the pi. So in 222, we'll make you guys dive a little bit more deeply into that and learn that. I'm just kind of showing this to you now because this is important. This is filling some of the holes with our current theories. There's a saying that all models are wrong, but most of them are useful, which is true. Every model isn't perfect. There's something wrong with it that won't tell you everything, but they're still useful. So Lewis structures are useful, even though there's things that are wrong about them. Molecular orbital theory is very useful, even though there are things that don't make sense sometimes. All right. I think that's all I want to do. I don't want to get crazy. So here's B2, which I just showed you, paramagnetic. Here's cyanide ion, and you could do cyanide ion just as easily. 14 electrons, 1 extra electron because of the minus, and it turns out cyanide ion is, I believe, diamagnetic. Yeah, with a bond order of 3. That we could calculate using Lewis structures too. And I don't want to kind of go over the why, but the MO theory is so useful for explaining things like absorbance spectra. So the stuff we did in lab 8, or 7, that's what it was, where we looked at absorbance spectra. So when does a molecule absorb visible light? So how does a molecule absorb visible light? Well, that's how you would use this to explain it. Because most visible light absorptions come from what is called the lowest occupied, the highest occupied HOMO, the highest occupied molecular orbital, transitioning to an electron to the lowest unoccupied molecular orbital, the LUMO. So if you become a chemist, if you decide to take more chemistry, I should say, you'll study this a lot in physical chemistry, which is like third-year chemistry. You can calculate these energies pretty well as soon as you find the molecular orbital diagram. If you become a real chemistry person and you go to grad school for chemistry, you'll take classes, actually even before grad school, you do undergrad, you'll take classes where you learn this new math called group theory. And this weird math called group theory, you take 3D objects and you see what kind of transformations you can do that keep them the same. So like look at a tetrahedral methane molecule and you can rotate it 120 degrees along any axis, or you could flip it across a mirror plane, and you put all these possibilities together and it creates these MO diagrams for you. It's weird. It's weird math. It's all about symmetry. So this is all, this is getting into the realm of weird math and quantum mechanics again. So it gets complicated, but this is useful stuff. Let's put it that way. So we can start to explain, how delocalized electrons move around in a ring, even with molecular orbital diagrams. So here's that benzene. Again, don't worry about it. I'm just kind of showing you why MO theory is so important. Okay, and that's where the UV vis spectra come from. Okay. All right. I don't want to get any further than that because we're not going to have it on the exam. Okay. Hopefully that was somewhat interesting, but you'll at least have a frame of reference for learning what it's about if you take 222. All right, so next I wanted to kind of go over the practice exam. And I don't want to do all of it. I just want to do the parts that are more new for now, and we'll come back and do the older parts if we have time. So this is really old. This is sig figs. If you have an extreme desire for me to answer one of these, please let me know. But I'm going to skip these for now. This is all old. This is wavelength stuff. This is ionization energy, periodic trends, quantum numbers, subshells, electron configuration, unpaired electrons, small ions, atoms. This is all old. There we go. So 39 is where the first new thing happens. So, question, yeah.
Is the test gonna be in order of old and new?
I can't guarantee it's going to be in perfect order, no. But you'll have a little bit of everything. It's going to be comprehensive, yeah. Question, yeah.
After we solve those, can you solve question number 3? I'm kind of confused about it, the one on the first page.
Okay, let's do that first, because it's fresh in your mind. All right. Oh, it's a conversion. No, it is. Okay, conversion. So this is a good question because these are always a little difficult when you have squares and cubes. So to set this up, the best way to do it is dimensional analysis. And you kind of have to recognize, well, what do I start with? What do I end up with? An easy way to kind of sort out what you have is anything where you have a unit in the numerator and the denominator. That's a conversion factor. So dollars in the numerator, inches squared in the denominator, that's a conversion factor. So I'm going to use that as a conversion factor. I'm going to start with 17.7 centimeters squared. And what I'm looking for is the cost. So in dollars, I guess. Yep. So I actually need something that will convert centimeters squared into dollars. I have inches squared to dollars. So that's what this conversion factor does for me. So really, the first thing I need to do is convert my centimeters squared to inches squared. But notice I'm just writing inches and centimeters first, because what I'm going to do is I'm going to write what that conversion is. 1 inch is 2.54 centimeters. And to get the squared version, all I got to do is square both the numerator and the denominator. All right, so if I rewrite that, I get 1 inch squared. 1 squared is 1. 2.54 is 8 something. 2.54 squared. Oh, 6 something, excuse me, not 8. 6.4516 centimeters squared. And then now my centimeters squared cancels. And I want to get rid of the inches squared and have dollars. And that's where the new conversion comes in. So it's 325. Here, let's do it over here. 325 per inch squared. So for every 1 inch squared. And then that cancels. And I'm left with my answer. So 17.7 divided by 6.4516 times 3.25 gives me $8.92. I round it properly. Just see. Does that help? So yeah, this is the key part, is knowing to square both numerator and denominator. So you square the value and the unit.
Will we have to memorize like 1 inch is 2.54?
No, I think that's always been in the legend.
Okay.
The only ones you have to memorize are prefixes. Prefixes, that's it. There's a lot of people that don't know inches to centimeters. They're not familiar with inches, so it's fine. I look up conversions all the time, so it's okay. Okay, so 39. Which bond length is the shortest in the following compound? So there's a couple ways to know short. Bond order, longer the bond, the higher the bond order, the shorter it's going to be. But beyond that, it's just the size of the atoms. The smaller the atoms, the shorter the bond's going to be. So really, this question is asking for what are the two smallest atoms that are bonded together. So hydrogen is the smallest. So the question is between carbon, hydrogen, and oxygen and hydrogen, which one's smaller? So is carbon smaller or oxygen smaller? Well, you know that on the periodic table, as you go to the right, if you're in the same row, same period, to the right they get smaller. Oxygen's smaller than carbon. So the OH bond is going to be the shortest bond because it's made of the smallest atoms. Yeah.
So fluorine has a +7 core charge.
Mm-hmm.
I would have expected that to be, be a lot more attractive than hydrogen.
So fluorine is a smaller atom, but it's bonded to a carbon, which is big. So actually, I don't know. I think hydrogen's still smaller than fluorine, though. I believe.
That's fair.
I think. But even if they're comparable, putting something small next to a carbon versus putting something small next to an oxygen, the OH is better. Yeah, shorter. Okay. So 40, which of the following is the carbon to oxygen bond the shortest? So here's the other way, is bond order, and it's D. The highest bond order is going to be the shortest bond out of them all. They're all the same carbon-oxygen bond. I mean, they're not the same bond, but they're all the same atoms. So really, it's the number of electrons being shared. Well, the more you have, the shorter it's going to get.
Wait, carbon's actually smaller than oxygen. We're going back to 39.
Oxygen should be smaller. As you go left to right, the shell stays the same size, or the same shell, but they get more protons, so it contracts it more. Yeah. It's easy to flip those around. It's easy, I know. All right. Which of the following compounds contains the strongest carbon-nitrogen bond. So this is the opposite. Well, actually not the opposite. The strongest bond is going to be the shortest. But we're also looking for high bond order. So these are none of these are drawings. We're going to have to draw these. It's a little tedious. You could do the shortcut here. Given the fact that these are all period 2 elements, you can remember, hey, carbon has 4 bonds, nitrogen has 3 with a lone pair, oxygen has 2 bonds with 2 lone pairs, and the halogens have 1 bond with 1 lone pair. That's to make them the most stable. You can try to use that to take shortcuts in drawing these. But you can also just draw them the regular way if you want. That's going to take a while. But H2CNH looks like this. So take a cue from the ordering. There's 2 hydrogens on the carbon. The carbon's connected to a nitrogen, and the nitrogen's connected to a hydrogen. Remember that there needs to be 4 bonds to carbon, 3 bonds to nitrogen, so there must be a double bond here. And then for HCN, again, 4 bonds to carbon, 3 bonds to nitrogen. There usually is a triple bond here. C, 3 hydrogens on the carbon, a nitrogen, and then 2 hydrogens on the nitrogen. That's it. That's good. Carbon has all the bonds it needs. It's got a single bond between them. And then D, 3 hydrogens. There's a nitrogen, and then there's an oxygen. Carbon's got all the bonds it needs. Nitrogen needs 3 bonds. Oxygen needs 2. So that's it. So this one here is the strongest carbon-nitrogen bond because it's your triple bond. All right, I think 42 we've done it to death in the lab. If you don't recognize it by now, then you aren't looking at your corrections. But I gotta get back to your stuff. I forgot to do that. C is it. C is the correct structure. Only 2 of these are actually valid Lewis structures. So that one's a good Lewis structure, and that one is a good Lewis structure too. But this one has a negative formal charge on the nitrogen. This one has a negative formal charge on the oxygen, and it's better to have a negative formal charge on the most electronegative element. So C is the correct answer of this one. The rest of them are not correct Lewis structures. They don't have octets on the proper things, or they might have too many electrons.
Why is D not valid? Oh, because oxygen only has 6.
It has 6 on oxygen, yeah.
True, but doesn't E and nitrogen has like 10 electrons?
Oh, I didn't see that. That's wrong. Yeah, 10. That's bad. I guess they're all bad. I didn't notice that. Yeah. They're all bad. Yeah, so C is the only one that actually works. All right. So we have this molecule. What is X going to be? There's a couple ways to try this. You could try to draw everything out using the atoms that are listed there and see which one works. But honestly, the easiest way is to remember what a Lewis structure shows you. A Lewis structure shows you all of the valence electrons. So count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 total. So this thing has 26 total. And I know for a fact that 7 came from this chlorine, 7 from this, and 7 from this. So that's 21 electrons from the chlorine. There's 5 left. So those 5 must have come from that unknown element. And the only thing that could be is phosphorus. Phosphorus has 5 valence electrons. So phosphorus is it. 44, exactly the same problem. Count up the electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Minus 6 from the oxygen, that's 12 left. Minus 7 from the chlorine, that's 5 left. And we're left with phosphorus. Only phosphorus fits. 5 valence electrons. All right. which of the following species contain only single bonds? Another annoying problem, you have to draw everything out to see until you get to the right one. So the first one is cyanide ion, and I think we did that one, but if you do the Lewis structure properly, you'll end up with this, which does not have any single bonds at all. For NO+, here we can do that one real quick. 5 electrons from the nitrogen, 6 from the oxygen, and we're losing 1 from the plus charge, so 10 total. I've got 2 already drawn in. I've got 8 left. 1, 2, 3, 4, 5, 6. I've got 2 left. I'll put the 2 there. But that's not enough. I need more electrons on that oxygen. So I'm going to share that. I'm going to share that. That's the structure, Lewis structure. That's not a single bond at all. CO. We've done that one before. That one looks like this. O2, 2 minus. Do that one real quick too. So O2, 2 minus. There's 2 oxygens, each come with 6 valence electrons. And we have 2 extra electrons for the minus charge. So 14 total electrons. We'll put a single bond between them first. I've got 12 electrons left. 1, 2, 3, 4, 5, 6, plus the 2 here makes 8. And then notice that's perfect. I've got no electrons left. Everything has an octet. That's a single bond. D. That's it. That's the one that has a single bond only. If you did E, you would end up with this. So it has single bonds in it, but it's not only single bonds. There's a double bond too. Okay. Which of the following would be a resonance contributing structure for the compound? Notice that the lone pairs are omitted, that all of the atoms actually do obey the octet rule. So let's put them back in. All right? For this one that's listed at the top there, if everything technically obeys the octet rule, then this should have a lone pair on it, and this should have 2 lone pairs. It needs 4 total, 4 more electrons. This thing has 3 lone pairs on it. That's what it really looks like. And so the idea is, well, what's the other resonance structure? Well, why is the double bond on this side? Why couldn't it be on this side? Well, you can. You can put these back there, and we're going to instead move a lone pair from that side. So you get this. That is the other resonance structure, which is D. Okay. Generally, contributing resonance structures look exactly like the original, just the double bond is moving around. Okay. Things like these two are automatically wrong because you cannot move atoms around in resonance structures. Only the electrons can move around. Okay. Which of the following is best described with 2 resonance structures? This is another one where you have to kind of go through each one to figure it out, unless you recognize it. But let's start with the top, NO2. Nitrite ion, NO2 minus. 5 valence electrons. 2 oxygens, and there are 6 valence electrons each, plus an extra electron from the minus charge. That's 18 electrons. When I do the structure, I'll start off with 2 bonds. That's it. That's 4 electrons in those bonds. I'll do the octet rule for the outer atoms. If I'm going way too fast, please tell me, okay? I do the octet rule for these, this one. I've got 2 electrons left. I'm going to do the octet rule for the central atom. I only have 2 electrons, so those 2 And that's it. I can't add any more, but I haven't done an octet. So this is a case where I'm going to have to share. I'm going to move this lone pair to here, between them. But why did I do the left side? Well, there's another clue that there's resonance. I could have done it to the right side as well. And that is the other resonance structure. So I could have moved the right side lone pair instead. These are the two resonance structures, and that's it. That's the answer. So you don't have to do anything else. This is very similar to nitrate, NO3 minus. Nitrate has 3 resonance structures. This one has 2. 48. These are two technically valid resonant or Lewis structures, excuse me. But only one of them is correct in terms of stability. And so to find out which is correct, you've got to do formal charges. The formal charges will kind of clue you in as to which one is a better structure. So if I do the one on the right first,
Just a quick question while you're doing this. The partial charge is that we have in the quiz. Was that sort of funny looking
the
sigma symbol or something?
the delta, lowercase delta.
Oh.
I did it backwards, sorry. There we go. Partial negative, partial positive.
Okay. Okay, cool. And the positive should go on the side. That's more or that's less electronegative?
Yes.
Okay.
More electronegative element gets the partial negative, yeah.
Can we just draw an S? Like for that?
Oh,
Like for the partial charge?
I mean, if you got close to it, that's fine.
Okay.
That's fine. I understand. You guys don't. Not everybody knows the Greek letters very well. So even I don't, but I just know the ones that are useful. And I probably don't even draw them correctly, so or say them correctly. So for this one, formal charge. Technically, you calculate them all of them, but you can kind of ignore the hydrogens as long as it's got one bond. It's good. There's nothing else you can do. But if we look at this oxygen, 6 valence electrons for any regular oxygen, minus the number of lone pair electrons, there's none on that oxygen, minus half the number of bonding electrons, 2, 4, 6, 8. And you get a +2 charge, formal charge on that oxygen. And if we do it for the carbon, 4 valence electrons minus 4 lone pair electrons, minus half the number of bonding electrons. There's 4 in there. You get a -2. That seems pretty bad to me. Pretty large formal charges. If you compare it with the one on the left, you will definitely get a 0 formal charge in the carbon and a 0 formal charge on the oxygen. So that one's the correct one. And the explanation is because it's got no formal charges, and the other one does. Okay. I mean, even the sign of the charges, you want negative formal charges on the more electronegative element, and the negatives on the carbon. That's pretty bad. So that's very not going to form. That's not going to form at all. All right. So this Witter ion, which is a weird version of the amino acid where you have these permanent formal charges on things. There's a minus here, minus here and a plus here. But that's not what we're looking at here. This is the main part of the amino acid, and this is like what identifies which amino acid it is. So that's kind of the interesting part. This is the part that binds to other amino acids and make a long chain. So there is a positive charge in the nitrogen group on the amino acid backbone. That's this one right here. There's a negative here, which we can ignore. What about the nitrogens labeled 1, 2, and 3? Use formal charge to determine if they are neutral, negatively charged, or positively charged. So feel free to do it the way I showed you. You can also do shortcuts. And that is, nitrogen has 3 bonds and a lone pair. That's what makes it a 0 formal charge. 1, 2, 3, lone pair. That's 0. 1, 2, 3, lone pair, that's 0. That's not the normal one. That's got 4 bonds. So if you calculate the formal charge on that one, 5 minus 0 lone pairs minus 8 bonding pairs, you get a plus 1. So it's A. Nitrogen 1, 0, nitrogen 2, plus 1, nitrogen 3, 0.
So there's a CH2 in there. There's 2 CH2 and a CH. Like, is that common to have a compound inside of a Lewis structure?
So it's a shorthand. So instead of drawing the hydrogens as coming off of them, you just write CH2.
Right.
So really it's CHH coming off of them.
Okay.
It's a lot, yeah, even this is a little bit more than what we would normally write, but yeah, that's just shorthand.
Okay.
Okay. So 50 is one that I wouldn't put on the final, because it involves trigonal bipyramidal. So I said we wouldn't have that, but let's do it anyway just for practice. So I3 minus, I mean, at the very least you can do the Lewis structure of it on a final. I won't ask you to name it though. I3 minus, that's got, I think we did this in class, but whatever. 7 electrons for each iodine. There's 3 of them. And don't forget the extra electron from the minus charge. 22 electrons. So I'll put 1 iodine in the middle and the other 2 on either side. Bond to each. 2, 4 electrons used up. Octet rule on the outside. 1, 2, 3, 4, 5, 6 plus the 2 make 8. Octet rule on this side. 1, 2, 3, 4, 5, 6. And now we'll do the octet rule in the center. So this iodine has 2, 4 next to it. I need 4 more. That's 4 to give it a total of 8 electrons. And I think I'm done, but I'm not. Because I haven't used all the electrons. I have to show all of them. There is 2 more electrons in this structure somewhere. Well, everything has an octet, so what do? Well, I do the expanded octet. And I'm going to put them on an element that has d orbitals, empty d orbitals in it, which iodine does. The question is which one? Well, usually we make it symmetric, put it in the center if possible. But we're going to put the extra pair there. And there it is. That's the structure. Now, what is the shape? Okay, this is where you don't have to do it, but 1, 2, 3, 4, 5 domains. That is trigonal bipyramidal electron geometry. And the molecular geometry, when you have just 2 bonding domains, is linear. And if you can't see that, which is not a big deal again, remember this is the general shape for trigonal bipyramidal. You've got 3 around the middle, and then 1 up and 1 down. And really what this is the iodines are in the up and down position, and the lone pairs are in the around the middle section. That's why it's linear. So if ever the question is asking for what is the shape of the molecule, they're asking for the molecular geometry. If I want the electron geometry, you will specifically ask for that. Okay. It's needed for hybridization, of course, too. But if it's just a generic, what's the shape of this molecule? We're looking for the molecular geometry. Okay, that's what's here. So what is the structure of the SF3 ion? That's the molecular geometry. What do we? Oh, so I did circle an A for 50. For 51, SF3 plus. I keep bringing both erasers to that side. I don't know why. Oh. You guys are going to be so sick of Lewis structures after today. So SF3 plus. Sulfur has 6 valence electrons. Fluorine has 7. And there's 3 of them. Right, times 3. And I'm going to take away an electron because of the plus. -1. So 21, 20 plus 6 is 26. So sulfur, fluorine, I don't care about the shape right now. Like you can connect them however you want as long as they're connected to the sulfur. So 2, 4, 6 electrons, 20 left. Octet rule on the outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I got 2 left. Octet rule in the center. 2, 4, 6. I need 2 more. Perfect. That's all of them. Octet rule and everything. So this is the structure. The electron geometry is, since there is 1, 2, 3, 4 electron domains, the electron geometry is tetrahedral. That's not the question though. The question is, what is the shape? What's the structure of this molecule? We're looking for the molecular geometry. And so that's the subshape. So when you take tetrahedral and lop off one of those thick parts, you get trigonal pyramid or pyramidal.
So 50 and 51 are both exact, or like they're asking for the molecular geometry.
Mm-hmm.
And what would the electron geometry be? Like, how would you ask for the electron geometry?
What's the electron geometry or electron domain geometry? That's it. We'll specifically ask for it.
Okay, good.
So just in case you need to see it, remember tetrahedral has this general shape, right? But one of those positions has got nothing on it, just electrons. So if I remove that, the leftover shape is this pyramid shape, trigonal pyramid, okay? There it is, trigonal pyramid. All right, this is an old question. You guys are young. Back in the day, there was a crazy guy mailing envelopes of powder to political officials all over the place, and it had anthrax in it, or some of them did, not all of them. And so everybody was getting Cipro, give me a prescription for Cipro, which is an antibiotic, general purpose antibiotic. Pretty strong one though. And that's it, that's Cipro. So what's the question we're gonna ask? Well, what's the formal charges on those nitrogens? So it's the same question as last. It's a very long question for something very simple. So that's a 0 formal charge nitrogen. 5 minus 2 minus half of 6, 0. But it's got 3 bonds and 1 lone pair. That's a regular nitrogen too. 3 bonds and a lone pair, 0 formal charge.
Wait, sorry, I thought,
Oh,
so it's a 0 formal charge when there's 3 bonds and a lone pair. I thought it was just, oh, I guess, yeah, because it's bonding 3.
so for nitrogen, yeah. And like that's the shortcut, but if you want to calculate the formal charge, it's 5 minus 2 lone pairs minus half of the 6 bonding
Just,
pairs.
like, for a second, I thought the lone pairs were a bond, but they're not. They're lone pairs.
Okay, got it. Nitrogen 3 is exactly the same as the others. It's all 3 nitrogens. 0, 0, 0. So, pretty boring question for an interesting topic. But, you know, that's what was in the news, so it was like somebody was like, let's make a question about it. So which of the following molecules has a trigonal planar shape? I mean, you're just going to have, oh yeah, question, sorry.
So on the final, are we going to have the numbers like 2 and 3, how they were shown there?
Well, yeah, if I wanted you to identify, like these particular atoms, like write the formal charges, yeah, I put numbers. But it could be like a quiz where you just have to label all of them if they have any formal charges. Yeah.
Okay.
Okay. So 53. This is another one where you kind of have to do them all if you don't recognize them. But maybe you do, because there's a boron in there. Remember, boron is weird. Boron is one of those compounds that actually, or those elements, excuse me, that is okay with less than an octet. It doesn't need an octet to be stable.
Is it just boron and beryllium?
Yeah, boron and beryllium. Yep, those are the ones that are fine. And if you remember boron, maybe you remember the few structures we did. BF3 looks like this. and there's no lone pairs in that boron. So there's just 3 electron groups are on the boron. That's trigonal planar. That's it. That's the answer D. The rest of them are either linear or trigonal pyramidal. I mean, you can throw the linear ones out. That one's linear. That one's linear because there's only 2 atoms stuck to that middle one. So again, we're talking about what is the molecule shape. We're talking about the molecular shape. Yeah. So the rest of them are more complicated. 54, excuse me. Oh, let me circle the right one. 54. Which of the following molecules are planar? I like these and hate these at the same time because I understand how they're awful. But they're good for making you really think hard. So I have 5 different compounds, and 1 or more of them can be planar. So what's planar? Well, trigonal planar is planar. It's in the name. But there's also bent. Bent molecules are planar. Linear is planar too. Like, planar just means they're flat. So let's make sure. If you do all these, SO3, we'll do a few of these because they're tedious. Sulfur and oxygen are all 6 valence electrons, so 24 total electrons. I'll do that fast. This is going to look like this. And then I think there's going to be 2, 4, 6, 8. No, I did it wrong. Don't do that. And then you'll probably have to do something more like that. There we go. So that's what the Lewis structure for SO3. So you can see that this is 1, 2, 3 groups of electrons. That's trigonal planar. So 1's good. Sulfite, which was on the quiz today, has 2 extra electrons, 26 electrons. So I don't actually have to do the double bond in this case. I'm going to end up with something that looks like this. Although that's not the best shape. That's not the best Lewis structure, sorry. But this is the shape. 1, 2, 3, 4 groups. So trigonal is a tetrahedral electron geometry, trigonal pyramidal. So that's a valid Lewis structure. It's not the best Lewis structure. The best Lewis structure would be that. Yeah.
Wait, with the more than offset there in the sulfur?
Yes, because sulfur can.
It's in the period 3.
It's period 3. If you do, so if you don't do that, this has a +1, and these are all minus. But if you put a double bond in there, then that's 0, and these are minus. I know.
Yeah. I'm wrong, I think.
I mean, it's a small part. I'm not going to take a lot off of that. As long as everything else is correct. So 2 is definitely not planar. It's trigonal pyramidal. So 3, nitrate ion. We've done that before in lecture, so I'm just going to draw it. Nitrate looks pretty much exactly like that.
So you said SO3 is planar and SO3 2 minus is not planar?
Yeah. So SO3 is planar, trigonal planar,
I'm not.
because it's got only 3 groups of electrons around it. Nitrate, the same thing, trigonal planar. But sulfite, SO3 2 minus, has a lone pair of sulfur. So that's 1, 2, 3, 4 groups, tetrahedral, or if you discount, like the molecular shape is trigonal pyramidal. Trigonal pyramid. That's not planar. So 1 and 3 are planar, and we have that as an answer, but we also have 1, 3, and 5. So let's check 5 real quick. That actually looks just like the BF3, but instead of BF3, it's BH3. That works too. Trigonal planar. So C is the answer. These are all 1, 3, and 5 are all. Oops. That's better. 1, 3, and 5. There we go. Are all planar. C. Keep. Yeah. Go ahead.
You said planar can be like bent and linear, so if it's like instead of SO2 it was instead of SO3 it was like SO2, that would be planar too, or no? That's
Yeah.
not trigonal, or
Yeah.
what's
That could you could call that planar as well. Yeah. Planar meaning just flat in the plane, like a shape that fits in the plane of a piece of paper. I think.
I'm just confused because like it has a thing sticking out, so oh it's not. I guess it wouldn't be like 3D. Would it just mean not?
This
3D?
one right here, or this one?
The yeah, sure, one of those two.
Well, so I didn't draw it with the proper shape. I mean, this looks like linear across here. The true picture of this thing would be where you have these nice 120 degree angles. So that's like the right bond angles there. But again, this fits in the plane of a board. There's nothing that's sticking out or inwards to the board.
So when it means planar, it means that there's not, like in the molecular photo or whatever, the 3D photo, there's nothing sticking out.
Yes.
Okay.
Yeah. Planar is just flat. It fits in the two-dimensional. Yep. It's not my favorite question in the sense that the word planar is more of a geometry thing than a chemistry term. But. All right, metformin. If you're a diabetic, you might know this, but this is what diabetics take to lower blood sugar levels. I don't actually know how well it works, but
I don't have diabetes, but I just had like high blood sugar. I was like always hungry, so I used to take it.
And it works or not really?
Well, I was supposed to take it, and I just like was slacking, so I don't know.
Okay. I actually have no idea how it would work either, but apparently they prescribe it, so it must do something. So what is the geometry around the nitrogen in the center, the N3 nitrogen, this one right here? So it's a Lewis structure, so everything's there. You just count the groups. 1, 2, 3, 4 groups. The electron geometry is tetrahedral, and that's what we're asking for. Electron domain model to predict the geometry. So it's tetrahedral electron geometry. The molecular shape is not tetrahedral. It would be trigonal pyramidal around the nitrogen, but we're asking for the electron domain geometry, okay? So that's just counting 4 groups, 4 domains around the nitrogen, tetrahedral. Okay. Oh, 56 is a great question. It's an awesome question. So, we have a molecule drawn up there. There's a Lewis structure there. And on the table, we've given you, and read the header carefully, this is not the bond length of this. This is the average bond length of a SO single bond and the average bond length for an SO double bond. What would you predict the SO bond length between these two atoms to be? So the trap answer, if you just circled A, you'd be wrong. All right, because a lot of people will say, oh, it's a double bond, it's 135, that's what it is. No, it's not. Because what you fail to recognize if you answered that is there's resonance in this structure. So the S and O double bond could have easily been drawn on the left side, like that. And so what is the true picture of the molecule? It's a combination of these two resonance structures. So remember how to do this. We're going to calculate the average bond order. So sometimes it's in this particular structure, it's a double bond here, bond order 2, and it's a single bond here. And let's average that across 2 bonds. I get 1.5.
Wait, I'm sorry, how did, so there's 2 on one side and 1 on the other, like.
So you look at one structure only, and you look at all the bonds that are involved, and these are the 2. So one of them's a double bond, bond order 2, the other one's a single bond.
Okay, so
And
it's because that's a double bond and that's a single bond, not because there's two bonds, right?
Well, I'm dividing it by 2
Oh, okay.
bonds total.
But, yeah, I just meant like.
Yeah, so this is the bond order 2 bond, and this is the bond order 1 bond. Yeah. So what this is telling me is that the average bond here is not 2 or 1, it's an average of 1.5. So I would predict that it's somewhere in between these two. It's a 1.5 bond. It's not a single bond, it's not a double bond, it's in between. And the best one that's in between is probably the C, 146. I mean, how do you figure that out? Well, let's do the average. 157 plus 135. We'll divide that by 2. And I think you get 146. That looks like it makes sense to me. So.
Yeah, you get one.
Yeah, so 146. That's what I would predict the bond length in SO2 is going to be. In fact, not just this bond, that bond too will be the same, 146, because they're the same. So again, the true picture of this molecule is not this, nor is it that. It's something that looks like, oh, well, there's one pair there, but there's a 1.5 bond, which you can't really draw with a Lewis structure, but that's kind of how you would imagine it. Okay?
Oh, actually, yeah. So on the subject of that, on our quiz, we
Uh-huh.
had a molecule that had resonance, the SO2. I think it was SO2.
Yeah, yeah,
So-
SO3, yeah.
Oh, yeah.
Oh, the selenium one too, yeah, yeah.
Or that's one that I was thinking. So for the half bond, do we include like 1 electron or something like that in the valence shell of the
Well,
oxygen?
you shouldn't draw half bonds in Lewis structures at all.
Okay.
So for a proper Lewis structure, you have to show the 2 different resonance structures if you're going to do that.
Okay.
So yeah, the whole resonance hybrid is not a proper structure. It's just, you just have to picture it in your head that way. Okay.
So that's sort of just like not technically any particular style of
Yeah,
bonding.
yeah. And again, that's why valence bond theory is great, but it's not perfect. You know, the whole resonance structure idea is a band-aid of, to understand what's really happening.
Yeah, okay, fair
Okay.
enough.
Okay. Now let's contrast the last question with the next one, because they're very similar but yet different. So we have these 2 structures, and they are different resonance structures, but they're not equal resonance structures like we saw in the last 2. They're significantly different. So which one is the better structure? Which one is the larger contributor to the hybrid structure? So again, that's just saying which one's going to be the dominant structure, which one's going to be the one that the molecule is most stable as. And if you picked B, you'd be right. And how do we know that? Well, you calculate formal charges and everything. So having a formal charge of a -1 on the oxygen is better than having a formal charge of a negative on the carbon. So if you calculate it, everything's 0, but this carbon is a -1, and this oxygen has a -1. We want negative formal charges to be on the more electronegative atom possible.
Just, sorry, so obviously carbon bonds 4 times, so since carbon and carbon is like a double bond, but those carbons, like, I know you can do the calculation, but I'm trying to do it without the calculation, it would be 0 because it's a double bond, or would I have to do it because there's only 2?
This
So
one right
the
here?
For B,
Oh, here?
yeah, like.
So
carbon-
there's needs 4 bonds, so the double bond counts as 2.
Oh,
So 1, 2, 3,
so-
4. Perfect.
Okay,
Is-
so
is it-
so that's 0, so I don't need to like calculate.
You don't have to. Yeah, you can take the shortcut and just, say it's fine. But this has 3 and a lone pair, so that's not normal. If you calculate, you'll find out to be -1. So this is the dominant structure, meaning if you're going to find the molecule, it's going to probably look like this, most likely. And then, what would you predict the carbon-oxygen bond length to be? Well, it's not going to be like before where we average them out, because this is the dominant structure. So it's most likely going to be closest to a carbon-oxygen single bond. And so I predict that CO bond is going to be 143. and that's it. So I did circle this one with B. Yeah. So make sure you understand the difference between those two problems, because it's like the two best contrasting examples you can get. Not the best, but pretty good. 59. Calculation. So it's not all visual, it's not all drawing pictures. How do you calculate an average valence electron energy? It's not hard. Just got to remember what it is. An average valence electron energy is kind of like an ionization energy, but instead of just removing the outermost, easiest to remove electron only, we're averaging out all of the valence electrons. So for phosphorus, I mean, let's write out the electron configuration just to be clear. For phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. Count over 3 to get the phosphorus. So these are your valence orbitals, which means these are your valence electrons. So those are the ones we're going to average together to get our AVEE. And these are the energies required to remove an electron from those subshells. So notice there's 2 electrons in the 3s. So for the first electron, it takes 1.95 megajoules of energy. For the other electron in that shell, it also takes 1.95 megajoules of energy. Those are the 2 electrons in the S subshell. Let's look at the P subshell. There's 3 of them. 3 electrons. So for the first one, it takes 1.06. All right, I'm getting these numbers right from here, the table. For the second electron, it also takes 1.06. For the third, it's 1.06. So I'm not saying we're doing the first and then the second and then removing the third. I'm saying we're taking off one or the other or the other. Yeah.
Can you just do like 1.95 and then just have like a 2 next to it?
Yeah, times 2.
Okay,
That's fine too. Same math. And then we're dividing it by a total of 5 electrons, and I think you get B, 1.42.
So if this were selenium, it would be the same except for it would be 4s2 and 4p3, and if we
Yeah.
also have a full 3d shell, the d shell would not be part of
No,
that.
you only include the D shell as valence for transition nodes.
Oh, right,
Yeah.
transition.
Yep. Okay. In which molecule will the partial charge on fluorine be the most negative? So fluorine is the most electronegative element, but when it comes to a partial charge, it's all about the difference in electronegativity. So the greatest partial negative, and of course the opposite, the greatest partial positive, will come from 2 very different electronegative elements. So if fluorine is the most electronegative, we want the least electronegative. And in that list, silicon is farthest to the left, farthest down in the periodic table. So SiF4, each of those bonds will be have very, very partial negative fluorine on them. So the difference in electronegativity is greatest between silicon and fluorine. And so you'll have the most partial negative fluorines that way. Right, if you had 2 fluorines put together, yes, they're both very electronegative, but they're equal electronegativity, so there'll be 0 charge. Okay, 61, and I emphasized this last lecture. To find the hybridization, you just need to know the shape. So anything that is trigonal planar is automatically sp2 hybridized. So trigonal planar gives you sp2. The other ones, sp comes from linear, and then sp3 comes from tetrahedral. That's it. So find the electron geometry, and you'll know what the hybridization is based on that. So how many carbon atoms are sp2 hybridized? I'm going to actually flip this up. And I did this in the other lecture so somebody wants to watch the video, it's in the previous video. But, this is where you take into account line drawings. Line drawings are tricky because it's missing a lot of stuff. So it might help when you get a line drawing to draw everything in, just to make sure you know what you're looking at. So these are carbons. Carbon is going to have 4 bonds to it. So if I only see 3 bonds, right, this carbon has 1, 2, 3, there must be a missing bond to a hydrogen. In fact, there's hydrogens all over this thing. And a hydrogen there. There's nothing here. This already has 4 bonds. 1, 2, 3, 4. But there's a hydrogen there, hydrogen there, hydrogen there, hydrogen there, hydrogen there. Ooh. Okay. So now, how many carbon atoms are sp2 hybridized? We're looking for trigonal planar. That's what sp2 hybridized means. So anything with 3 groups of electrons. 1, 2, 3. That's sp2. That's sp2. That's sp2. That's sp2. That. Pretty much all of these carbons are sp2 hybridized. All of them. They are all trigonal planar electron geometry. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them.
So how would you know if there would be valence electron, or I mean lone pair electrons?
You have to draw them in yourself. So in a line drawing, you have, if there's going to be a formal charge somewhere, you have to show that. You can't you can't not show it.
Okay.
So assuming that there's no formal charges anywhere, that oxygen has to have 2 pairs, or 2 lone pairs on it. Yeah, that's another thing that's not shown.
So let's say that right one with the number sign underneath it, let's say that one had a lone pair of electrons, would they just put 2 dots next to that?
Yeah, they show the lone pair, or they would show that it has a minus charge, formal charge on it. Yeah.
Okay. Okay. Cool.
Yeah, the line drawing you have to put one or the other, otherwise you can't guess. You know.
Yeah, fair enough.
Sorry.
Yeah.
So there's 9 carbons and there's, do you just like imagine the Lewis structure and then that's how you determine the shape?
Yeah, I mean we can even draw in all the carbons,
Yeah.
but there are 9 carbons, and it's a coincidence, but all 9 carbons are trigonal planar too.
So that's my, like, how did you know? Did you just?
Well, so I quickly, but you go to each one and you say, well, how many groups of electrons are next to each one? So this carbon has 1, 2, 3. This carbon has 1, 2, 3. They all have 3. None of them have anything different. So even this carbon here, 1, 2, 3 groups of electrons around it. So they're all trigonal planar. So they're all sp2. So how many sigma bonds are there? And this is where drawing everything in helps. Sigma bonds. Anybody know?
What does that mean again?
So a sigma bond is the kind of bond overlap where the orbitals do the end-to-end overlap. So the easy way to think about it is every bond has, the first bond of it is going to be a sigma bond.
Wait,
So-
pi bonds or sigma bonds?
Sigma bonds.
Uh-huh.
Every bond drawn in a structure starts off with a sigma bond. Right? So, I mean, they come from, 2 s orbitals overlapping like that. That's a sigma bond. They come from 2 p orbitals overlapping like that. That's a sigma bond. It's just an end-to-end overlap. You can do hybrid orbital overlap. So, an sp2 with an s orbital. That's a sigma bond. So they're all of the first bonds in every single structure is going to be a sigma bond. So there's actually 18 of them. 1, 2, 3. So let me do this first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
And is that because? Well,
Oh, I skipped one. I'm sorry. I skipped the pi bond. My bad.
oh,
Yeah, what were you asking,
wait,
sorry?
that's the sig. Wait, are we doing pi or
Yeah, I'm sorry, I skipped the pi bond question. That's sigma.
Okay. Yeah.
So you want to finish your
Maybe
question?
we do the pi one.
Okay, so let's do the pi bond. I'm sorry, you guys were looking at that. How many pi bonds are there? Yeah, I mean, you just look at the double bonds. 1, 2, 3, 4, 5. 5 pi bonds shown.
So is one bond sigma and two bonds pi or something?
So a single bond is always a sigma bond. A pi bond is 2 bonds. Sorry, I said that wrong. A double bond. The fact that it's double bond means it's 2 bonds together, and that is always a sigma with a pi. So double bonds are 2 bonds in one. It's a sigma bond and a pi bond together. Triple bonds are a sigma and 2 pi's.
Oh,
Okay. All right. What is the bond angle around the ox? That's another misprint. And I shouldn't have moved it. What is the bond angle around the carbon marked with a? I don't know what to say anymore because it's sharp #pound. There's another all sorts of names for
It
it.
should never be called hashtag.
Ah.
As a young
What is
individual,
this?
I do not condone that.
The original is pound, although sharp is music. No, I guess sharp is musical, so that's older. Yeah.
When's it now? Or never time.
Yeah, it's number sign. It's a sharp. The language is C#. There's tons of computer languages to that. Anyway, that is 120 degrees. 120 degrees there. All right, because we know it's trigonal planar. And it's not exactly 120, but it's approximately 120. And that's why there's a little tilde there, approximately. All right, I'm going to lose the picture now. So what is the geometry around the carbon atom marked with a star? An asterisk. Trigonal planar. We just kept saying it. So trigonal planar. That's A. Okay. Put these back down. We're almost done. What types of electrons are considered to be localized? So that's the big difference between sigma bonding and pi bonding. Sigma bonding always creates localized bonding, localized electrons. The electrons are stuck between those 2 atoms. So when I make a bond between a carbon and a hydrogen, there's a pair of electrons stuck there. They're localized. They're local to that area. Delocalized electrons, you can find them in pi bonds, because they can move around the ring like a benzene ring or something like that. So sigma are the kinds of electrons that are localized between 2 atoms.
just to be clear, anything that's just like in the s orbitals, any element that's like in the s orbitals is gonna be like a sigma, and then anything that's like s and p or d or something is gonna be pi and sigma.
You mean like the kind of overlapping?
Yeah.
It's slightly more complicated than that because we have to talk about hybridization too. So when you have a central atom and you've got those weird bond angles, the orbitals on that atom will hybridize. They'll mix to make those sp3 or sp2 or sp hybrid orbitals. So what's better, again, is all of the bonds that you see drawn in. The first bond
Oh, yeah.
is always the sigma bond. If there's a second bond there, like in the double bond, there's 2 bonds. That's a pi bond, and then the third bond, and then pi bond. Okay, I might skip that one because we've done it a lot. We're running out of time.
Can we go for something that's like
I was gonna do 72, but what were you gonna ask?
I saw something mention like polar and non-polar, and I just forgot what it was.
Oh. All right, we'll come back to this next time. Ask me after it all. I want to do this real quick because this was a new thing. So you could have to draw kind of bond diagrams, or like kind of how bonds or orbitals overlap to make bonds. So here we're going to draw the orbital representation for HCN. And you can definitely do it in multiple pictures. You don't have to fit it all into one. But let's start off with the Lewis structure. It looks like this. So what you should be thinking is, well, what's the hybridization? What orbitals are available? So the hydrogen just has a 1s orbital on it. That's it. This carbon is in the middle. It does hybridization. So the structure is linear across. So this carbon is sp hybridized. And then this one, the nitrogen, we're not going to do hybridization on the outside atoms. The nitrogen has the 2s and 2p orbitals available for bonding. Okay? So how would this look? Well, this carbon is going to have two sets of two sp hybrid orbitals. And so if I draw a carbon here, one of them is going to point this way. The other one's going to point this way. I should make them the same size. To be clear. My drawing still sucks. So. There we go. That's a little better. Still not great. So label everything, okay? sp, that's an sp orbital. There's two different ones. This one is pointing to the hydrogen. So we've got a hydrogen over here, and all the hydrogen's got is an s orbital. That's a 1s orbital. On this side, we've got our nitrogen. And what does the nitrogen have? Well, it's got the s's and the p's. Most likely, it's going to use one of the p orbitals to do bonding with. Because remember that nitrogen's electron configuration is 2s, 2p. 1, 2, 3, 4, 5. So it's going to try to do bonding with one of the p orbitals first. And the one that's oriented to do sigma bonding is the p orbital that's pointed this way. Like that. So this is a p orbital, a 2p orbital. All right, so we've got a sigma bond here. And we've got a sigma bond here. So that's the first part. Now what's left? Well, we've got 3 bonds here. We've only shown one of the bonds between the carbon and the nitrogen. So the rest of them come from the unused p orbitals. So in addition to 2 sp hybrid orbitals, there's going to be 2 leftover p orbitals. Right? Because carbon comes with an s and 3 p's. The s and one of the p's mixed together, I have 2 leftover p's. And so they're going to be oriented this way and this way. So I'm going to draw them down here, just separately. So one of the p orbitals will be like this, and the nitrogen, let me make this a little closer, just to make it clear. The nitrogen will have a p orbital also looking like that. And notice that these are overlapping in 2 spots. That's a pi bond. And these are p orbitals from the carbon and the nitrogen. And not only does this happen once, this happens twice.
Wait, so what is the right one, the one at the top one or the bottom? What's the?
They're both. So this, overlay this on top of this. They all happen at the same time.
So which one would be the right? Oh, both are?
They're both, yeah. So in addition to these orbitals, there's also these. And I just wanted to draw it separately so it didn't get crazy looking. Does that make sense?
So on a test you'd accept like either,
Separate images. That's fine.
either one or both?
You'd have to, if you need to show all the bonding, you need to show all of it. And so there's, and I wrote there's 2 sets of these. So in addition to the ones that are going up and down this way, there's the ones that are going in and out of the board this way. And they're doing the same kind of overlap as these right here.
Okay, so the sp hybridization between the carbon and the nitrogen
Uh-huh.
is between 2 p bonds, but the idea that the carbon's sp hybridization is because it's the central atom, I guess, and it's combining with its own s orbital to make that second sort of sp hybridized.
Yeah, it has to do sp hybridization, because if it used the p orbital that nitrogen's using, the same one, it could only do bonds to one side. Because remember, you can only fit 2 electrons in orbital, and you can't share, like I can't. So this is a p orbital, and I think what's confusing is, oh, there's a lobe pointing backwards too. Why can't we do the same thing for carbon?
Right.
But I can't use the same orbital to bond to 2 sides.
Huh.
Because you can't, because you can't have enough electrons in that one orbital to do sharing. Because the idea behind overlap of orbitals is you're sharing electrons.
Yeah.
And I need to share electrons with the hydrogen and with the nitrogen, and I can't do
Yeah,
it
you
with
only have
both.
2 per orbital.
Yeah.
Oh, I
Yeah,
understand.
and so you have to do hybridization so that I have one orbital pointing that way, and one orbital pointing that different orbital pointing that way.
Okay.
Yeah.
I'm gonna
The
say yes.
the short answer is the central atom gets the hybridization. That's it.
Okay.
How are you gonna draw the p orbitals that are coming out of the plane?
If you literally write there's two
Just two
sets,
sets?
that's fine.
Okay.
And I'll get it. Or just say it's the 2 sets. Second one's perpendicular.
Okay.
That's probably fine. If you want to try drawing perspective, I
I would
can
not
accept
know
that
how.
too. I try. Sometimes it looks okay. Sometimes it doesn't. So, all right. I may not ask a question exactly like that because that's a really tedious one to grade. So, but there may be pieces of it, right? There may be like draw this kind of overlap, and you'll have to understand what that looks like. Okay. All right.
I'm not an artist.
Yeah. I'm not a confident artist. I could draw, but I'm not great at it.
You're good at drawing circles. Your circles are very.
You can also be confident.
Only if they're the right size. If they're bigger, then they get really weird. Yeah. Any questions? Anything else? I mean, there's plenty more in this final to practice. The key is up there. There is no outline, but just use the old ones, and the stuff that we just went over is pretty short, so I think you can catch up. Follow up.
On Tuesday, you need to be here at 12 or 12:30.
12:30. It's the same exact time as a regular lecture, and that's it. We'll just meet for the class. Done. No lab, nothing else that week.
Will you have your office hours on Monday, or no?
I will be here. Yes.
Okay.
So
Yeah, that's true.
I think I will be here on time.
Unless you're not
So
taking
I
Okay.
should be here.
Okay, cool. Thank you.